Bismillahirrahmanirrahim. Good morning. Assalamu alaikum. Gentlemen, how are you? Okay, today we will start the design of isolated footage. That might be our last lecture, and probably from the next week you will be going for your examination. So this is our last lecture. If you have any query, you can just contact me. I would be available every time, inshallah. So here we start from the footing. So the point is, what is actually footing means? Actually, it is defined as a structural component of reinforced concrete structures that transmits building loads. It's very important to know that transmits the building loads, where it transmits to the supporting soil, and these loads are carried by columns and walls. These are three important things to know from the footing definition. That is a structural component that transmits the building loads carried by columns and walls to the supporting soil. So a building consists of columns, walls, beams, etc. All these things, and so it transmits. We have to finally transmit all these loads. So the building, if you remember, just give you a simple sketch like this one, let's say, and similarly here we have column. Just giving you a simple sketch. Here is one story, first story beam or slab. Here is another story beam. So all the loads working applied on these slabs are transferred to these walls or columns. Means load transfer mechanism is like this one. Loads from this area moves to these columns through beam actions. Means beams transfers these loads to the columns. Columns further transfer these loads to the lower columns, and these columns further transfer these loads to these footings, and footings spread all these loads to the surrounding or supporting soil. So this is basically load transfer mechanism of the soil. Footing, there are various types of footings, but we will be studying one of them. We will not be going to study all the types of footing. There are various types. It may be categorized as shallow footing and deep, shallow foundations and deep foundations. Normally, deep foundations consist of pile foundations. So let's see here. Start from here. One thing is called, this is isolated spread footing. This is isolated. Isolated means for single column. This is an isolated for single column. So this is, you see here. Here is a column that's supposed to be here. This is a column, and this area is the footing. This one is the footing width and the length. So this is the footing that transfers the column loads to the surrounding sides. Similarly here you can see a wall footing. So this is a wall moving on, and that's all the wall. There is a foundation at the wall. If you see that this elevation of the wall, so this is a wall section, and here is the footing where wall is resting. In normal observation here in local areas, you might have observed the wall footings are stepped. This is not all is not at the, or you maybe in you have tried in your the previous classes, and when you go for the foundation design or in your estimation and construction, maybe you have this kind of step footings. Hope you will remember. You have this kind of step footings. So you have different steps like this. Sorry, unable to understand, draw this carefully. So you have step footing. These are called step footing, but this is single step footing. There is no multiple steps. Further, you will see next here some kind of the footings are also step footing. What are these kinds? So this is a rectangular footing. So this is a rectangular footing. This is a combined footing. You see, this is a combined footing for two columns together. Here you see it's one column, and for this it's this kind of footing, spread footing, isolated spread footing. But for this column, when we go for the rectangular combined column, then it would be like you extend that, or if you just assume this one as column and this one column here, if you assume and other column you assume here, and you take this as one here, this will serve as your elevation for the combined footing. This whole wood can serve as the elevation of the combined footing of this case. Okay? Similarly, combined footing further have this kind of. So in footing concept, there is very important thing to know. One thing is the property line. You see, this is property line. There is no mention of property line in these three footings. Property line is basically, let's say this is your plot, this area is yours, and someone else is at this neighboring area. Someone else is at the neighboring area. But if you have some column here at this location, you have some column. For this footing, you cannot go beyond this property line because your property is to this line. Beyond this, there is no right of you to use that space. So you are restricted to stay within this area. So within this area, this is property line. So this is your property toward this side, and on the other hand, this side is not your property. So you don't have any right to use that space. So you have to be limited within this area. Staying in that area, you have to design a footing. This is a combined footing in the case when you are at the corners, at the edge column. When you want a combined footing of edge column, this is an edge column and this is an internal column. So in this case, you have to take care of this property line concept. Similarly, further, again here is property column, but this is a combined footing. In this case, this is we cannot say actually rectangular. Trapezoidal would be the very okay, somewhat better than. It's not exactly triangular, rectangular. In this combined footing, you see here, it is assumed that the loads acting at column A is less than the load acting at B. Alright, are the loads transfers to column A are lesser than the column B. So that's why column A requires lesser area of transmission and column B requires a more area. Similarly, here is the strap or cantilever footing. It's called strap and cantilever footing. So again here you see this is the property line. We are not going beyond this property line. We have to stay within the limits of our property. We cannot go beyond our property limits. So this is another type of footing. This one is the mat footing. When you have closely spaced columns, or for each column you comes to be, you have the areas are very closer spaces or closer column. Then what you do, you put a hole or a mat footing or the raft footing, you can say. So all the columns put together, all the footing is designed simultaneously for all columns. We have we provide all the base, the uniform or the combined footing. Some kind of concept is combined footing, and we don't design for every single column. Here for this kind of case, we use all the columns and all the footings together. And here one is the pile foundation. Pile foundation is normally you can observe them on this pile foundation for heavy structures. I mean multi-story structures, or simply you can observe these pile foundations in case of the bridge piers and all these bridges. Normally, most probably in the bridges. So in this case, normally this top portion is weak soil. So we have to extend our piles towards the bearing stratum, hard strata, where our piles can transfer the loads. So transfer of loads of piles, there is two ways. Either they can transfer the load by their tip, this is called tip, or they can transfer their loads by this shaft, their shaft or skin. So there's a different debate about this, how which pile can transfer the more loads and what. In fact, there are so many types of piles also, and their transfer mechanism is also variable. Some piles transfer their loads through their skin action or their shaft, and some can be used to transfer the loads through the tip action, or in some cases both actions can be recommended. So all these piles are supported with one pile cap, and pile cap consists of piers or columns. This is called pier or column. So further supporting on the structure is further supporting on this one. So some different steps, design steps for footing. Basically, first of all, you must know what is the footing requirements. I mean, footing requirements mean the expected loadings, what kind of soil structure is available, where you are going to design the footing. So these are two important things to know before we go on the footing design, the nature of loads, the values of the loadings, and then the soil structure there. Further, you can decide which footing you are going to design. Either you want a shallow footing or deep foundation. Deep foundation, I tell you earlier, that comes under the pile foundations concept, and shallow footing are the normal footings that they don't have the very more depth. They are normally lower depth foundations. Secondly, third thing is the geometry selection. Which kind of you know sorry which kind of geometry of the of your footing should be. So these are based on this. There are 3 or 4 factors to study. One is bearing capacity or the bearing pressure of soil. So you have to compare with the calculated bearing pressure, and the calculated bearing pressure means how much pressure your footing is going to exert. This one is the calculated and allowable bearing pressure, and allowable bearing pressure is how much soil can support. Let's say this is sorry let's say this is your foundation, and this one is soil below here. So this soil, how much this soil can support the pressure, how much this soil can bear the pressure, this is allowable footing of the footing bearing pressure, how much soil can support. Secondly, the thing is the how much calculated mean how much pressure is being applied on this footing. Similarly, another parameter is the footing settlement. So footing settlement is basically settlement of the soil. Basically, it is the settlement of the soil. So that is, we have to determine if the load increases and at which value of the load, the how much settlement in the soil can take place. So this is what we determine based on the determination of supported soil nature, and normally in practical design these things are calculated. This is in the settlement and all these parameters by geotechnical engineers that recommends that this much settlement is expected in this kind of soil, in this kind of area. Similarly, another thing is slide resistance capacity. So if you are supporting some kind of in hilly areas, that is inclined path, inclined way, elevations variation is there on 2 different slopes. Let's say this one is the area, and your one column is working over here and other column is over here. So you are connected these columns by these beams. So there is possibility of some sliding either here or either here. So in this kind of systems, we need to understand the sliding capacity, sliding resistance capacity, how much sliding resistance capacity we are providing, whether the design would be able enough to resist all these kind of expected sliding. Similarly, for the overturning concept is important as well. So whether it would be able to resist the overturning, and the complete design of this one is actually discussed in ACI course, that is chapter 15, I guess, in ACI course. So here we start from the we will be studying only design of isolated footing. Yes, we will not be going to study the design of combined footing and the deep foundation. We will be studying only design of the isolated footing, and in isolated footing we will study 2 things. One is square footing, another one the rectangular footing. That's very simple one. Only one square footing and one rectangular footing. So for isolated footing, you see this one is a column. So this column, for this column, the footing can be square, footing can be rectangular. For this kind of column, one column, footing can be circular and octagonal. So any kind of footing might possible for one column. If you are going to design an isolated footing, so an isolated footing means there is one column, and you are going to design footing for one column, and this footing can be either square, can be rectangular, can be circular or octagonal, whatever you like, and whatever is feasible for you. But for reasonable thickness, actually there is one kind of parameter that governs actually their shapes and the thickness, the levels. This is thickness. How much thickness is required? Thickness is determined, or the thickness is the assumed based on the acting. Thickness is decided based on the working loads. How much load applied loads are being applied. So for this, how much resistance we have to create. So for that, in that case, we decide the thickness of the slab. Normally, if something is a reasonable thickness like 12 inch, 24 inch, maybe up to 24 inch is okay, I guess. So if in the case of 24 inch thickness, then you can go for single slab footing. You see here, single slab footing. This one is the single slab. This one is the single slab footing. So in case when you have the higher thickness is more, like let's say it's more than 24, like 36 inch and something, 48 inch, 4 feet I mean. So in this case, what we do, we go for the stepped footing concept. Actually, step footing, what we do, the central part where beam column is acting on, we provide steps there, so we can extend the total thickness. So total thickness in this area increases. See, total thickness at this column vicinity increases, and at the ends we keep one step. We may provide 2 or 3 steps. Here it is 2 step, or step footing you can say it is 2 steps. So some conditions may require us to provide 3 steps. As you remember in your construction estimation things stuffs, you provide 3 or 4 steps in your brick masonry foundations something. So similarly, we can provide here also, but that depends upon the requirement whether we are required to do or not. Third one is, okay, that's occasionally required. That's not it's not very common, but occasionally it's required. That is sloped footing. In sloped footing, what we do, similarly again, like the step footing, the center is given the highest maximum height, maximum depth. The maximum depth is given at the center, and it is reduced to the a certain value, or the single step slab footing from the bottom. So it's go on decreasing towards the outer ends. So this is a 3 different modes of single footing, or the isolated footing. So that is single slab footing, step footing, and the slope footing. There one important thing, most important maybe in the footing design, is the shears, the shear strength. So in shear there are two things. One is called one-way shear or beam shear. Shear in footing is 2 types: one-way shear or beam shear, and other one is two-way shear or the punching shear. So first we will discuss the one-way shear. What actually this is one-way shear. So actually one-way shear, we have to identify the critical sections. Critical sections mean where shear strength is more and where cracking can occur. We have to locate that critical sections. So critical sections located at a distance D, from the face of the column. So in our design, we have to find out. Let's say this one is diagram. So this is a column. You see, this is our column. So for this kind of column, the critical section where shear strength would be more or the maximum is located at distance D from the face of the column. So if you see here, this is the face of the column. This one is the face of the column face. So the critical section is somewhere here. This is at distance D from the face of the column. And interestingly, this D is actually the depth, effective depth. This D is actually the effective depth. Don't get confused of this D. Actually, this D is the effective depth. So we can say that the critical section of a isolated footing in one-way shear occurs at a distance equal to the effective depth of the beam there, or the the effective depth of the slab here. Further, you see here in kind of plan view, this is just other view. So this is your column. This is the distance D. At distance D. So at this line, the shear strength is occurring at this line, 0.11. This section 11, there is the shear strength occurring, and this point is at distance D from the face of the column. You note here, it is at distance D from the face of the column. And if you say this one as the the column dimension, and you see this column width is represented as a. I just want to understand you the different dimension. So this column dimension is the a. So this whole column dimension is a. Width is column width is a, and the total length of the footing is L. So if we see here, so from if we are starting from here, actually this center line, from this center line to this distance, how much it would be? This would be this D plus this A by 2. This is A by 2 from here. Alright. So actually we are not concerned this one. We are interested to know this distance from here to here is D, and we need to determine this distance is how much this distance is. So this distance would be, this is L. L is from the whole one. So from the center to the extreme, this would be L by 2. Clear? So we need to determine this distance. This distance would be equal to L by 2. So this is L by 2. L by 2. If we subtract from this one A by 2 from L by 2, so we would be at this distance here. So this distance is L by 2 minus A by 2. So now we need to determine this distance. So we know that from here to here it's L by 2 minus A by 2, and we know this distance in between it is D. So this remaining distance would be L by 2 minus A by 2 minus D as described here. See here, L by 2 minus A by 2 minus D. Okay, further the value of Vu1 for one-way shear, we use the shear strength 1 along the 1-1 section. This one section 1-1 is equal to the net soil pressure. So is equal to the net soil pressure. This is the vertical soil pressure. This one is the vertical soil pressure. So the shear strength produced at this section along this section is equal to net soil pressure multiplied by this hatched area. This is the hatched area, right? So this we need, and the shear strength at this section 1-1 would be equal to the net soil pressure, that is here QU, times this the hatched area. So if you find to determine the hatched area, you need to know this thickness that we just determined, that how much this dimension is, and then you have to multiply with this length, this dimension BW, width of the footing or width of the wall, whatever. So this will give you the hatched area. So you multiply the hatched area with the net soil pressure, you will get the strength, or the shear strength at this section. So ACI recommends an equation to determine this one. ACI equation 11.3. Actually, I put the ACI equations and reference properly today, because some of you sometimes expect, say, how come this 2, how come this 5, and all these things. So I decided it's better to put exactly the wording of the ACI. So Vu1, so the shear strength at one point is equal to 5 times of Vc. That's shear strength here. So it is 5 to under root Fc prime Bwd. So the shear strength here you can determine like this one. Actually, we have to find out this D. Sometimes we the D we assume preliminary in design, we take and assume a design value of D, but we have to always in design we have to compare our assumed D, assumed effective thickness, with our calculated thickness. So to find out the calculated thickness, we use this formula here, that is derived from this one formula. So this D will give us the calculated value. Then we will compare this calculated D with this assumed D. Then we will decide either our design is okay or not. Similarly, here is two-way or punching shear, and for two-way or punching shear, the ACI code recommends that this ACI code recommends that for two-way punching shear, the critical section where shear strength occurs is located at distance d by 2 from the face. Remember it, for two-way shear, this critical section occurs at distance d by 2 from the face. But for the one-way shear or beam shear, these critical sections occur at a distance d from the column face. So again, here is d, and the critical section would occur at a distance d by 2. Clear? So again here, the same is the column dimension here is a. So this is column section a. This column dimension is a, and d by 2 is this side, and d by 2 is this side. So total dimension would be a plus d by 2 plus d by 2 means a plus d by a plus d. Alright. So the remaining dimensions you can determine just simple L, and from this center, let's say if this is the center, so this side would be L by 2 minus a plus d, a plus d not, actually a by 2 minus d by 2, and similarly this dimension would be equal to L by 2 minus a by 2 d by 2. So the VU2 along this critical section periphery. So the shear strength determined to be expected along this periphery is equal to the net upward pressure, again QU, the net upward pressure QU times the hatched area. See this hatched area. So here VC is equal to 4 times of FC prime B naught D, and where B naught, what is B naught? Actually B naught is this perimeter. B naught, you see this dimension, one dimension is A plus D. So perimeter of this section, this portion, perimeter of this all portion is 4 times of A plus D. So this is the value of B naught in this equation you see here. So, and here is the concept of the punching shear, how when the shear strength here is not properly addressed, so the column would get separate from the rest of the things. You might have experienced these things in common life, because there is normally this punching shear phenomena occurs. So might be you might have observed this one. I don't know either you have done or not, but this is a very common phenomena sometimes. Further, for two-way shear and footing, when this was for the column footings, this is when rectangular footings subjected to bending into directions. The previous one we discussed, that was for the the square footings. So when rectangular footings are subjected into two directions, bending in two directions, and the long side, we need to work one more thing. The long side of the loaded area is more than twice the length of short side. Need to understand very carefully these two things. So when rectangular footing is subjected to bending in two directions, and the long side of the loaded area is more than 2 times or twice the length of short side, then shear strength, in that case the shear strength may be taken from this equation. So in that case, for this equation we can use this equation here. This is for rectangular case. Then here factor beta, actually here factor beta is the ratio of long side to the short side of the column. And please don't get confused this factor beta with the one we study in the flexural design of the beams, because I'm worried many of you are confusing the things and intermixing the things. So this factor beta is here in the footings for the rectangular section. Here is the long side to the short side of the column. Similarly, ACI equation 1134 is used to account the fact of decrease in shear strength with increase of B naught D. In case if B naught over D ratio keep on increasing, if B naught D factor, B naught is the perimeter of the hair. B naught over D, if that increases, then the fact is the decrease in shear strength is there. So in that case this formula is used, and in this formula one thing different is the alpha S, and this alpha S have 3 values, 40, 30 and 20. For interior columns its value is 40, For edge column this alpha value is 30, and for the corner columns this value is the 21. Clear? So there are three values of alpha, rest of all you know, and this alpha value is 40 for interior columns, is 30 for edge columns, and 20 for the corner columns. So critical section location D is taken the minimum of the following. So in this case the critical section value minimum of the following is that there are three formulas. You see this one is SI unit, this is an SI unit, this is FPS system. So these are three formulas actually basically, and we have put all these three formulas before. This is D is equal to VU over 5 EFC prime, the very first one for the square one. This is for rectangular, this is for rectangular. So normally the code defines that the critical section is taken minimum of the following. Minimum of the following. In case you are designing a rectangular section, you use these three or preferably first two, and you take the value of the minimum. If you are in design of the square one, you just take the first one, and you can find the value of the D. Similarly, this one formulas are for the system international units for in millimeter and extra. So now is the example for the isolated square footing. For isolated square footing, this is an example. Design a square column footing for a 16-inch square tied interior column. 16-inch square tied interior column that supports a dead load. The dead load mentioned is 200 K, and the live load is the 160 K. The column is reinforced with 8 bars. Column is reinforced with 8 bars, and the base of the footing is 5 feet below. Make it clear, the 5 feet below the grade. The soil weight is given, and Fy and Fc prime is given. QA, that is the the applied or accepted the upward pressure, the one QU we were mentioning. So one thing I need to remember, let's say this is your ground level, and this is your column footing here, like this one. Sorry. So there is one thing, the footing is 5 feet below. Footing is 5 feet below. Footing is 5 foot below mean from here to here this dimension is 5 foot. Understand? This dimension from here to here is the 5 foot. So if we assume this one or here to this distance 5 foot, let's say this is the depth of D something whatever. So this remaining here, this area is covered by the soil. This remaining area is covered by soil. So this soil load is also working on this footing. So this length, the length of this area would be equal to 5 foot, or the depth of that area, that depth 5 foot minus the depth of the footing. Alright. So let's move forward for the solution here. I repeat once again the statement so you make it clear. Is square column 16-inch square. Alright, 16 inch is the column dimension. The dead load is 200 K, live load is 160 kips. K means kips, kilopound per square foot. 8 bars are used there, and the footing is 5 foot below, as I mentioned earlier. What does this mean? This is a very important concept. You need to understand this one. You don't get confused with this concept, 5 foot below. And the weight is 100 pound per cubic foot. This is the weight of the soil. Further, yield strength and 28 days compressive strength are given. And Q is the earth pressure or the soil pressure is 500 pounds per square foot. So you see here, first of all, assume the slab or footing thickness. We take it as 24 inch. It means 2 feet. So we assume that the slab thickness is 24 inch. I mean this one is 24 inch. Alright, this thickness is assumed to be 24 inch in first step. Later, the next step is the effective depth D. This one, this is the effective depth D. So this effective depth D is equal to 24 minus. So this is actually the steel reinforcements here. The first layer of the steel. This is the steel top reinforcement. In the slab or in the footing, normally reinforcements are in two layers. If you ever observe the slabs or the footings, the reinforcements are never in one layer. These are always in the two layers in this pattern. So this one is the second layer. Second layer means the upper layer. So 24 is the total thickness of this one. Then we will subtract the concrete cover. And one more thing, if you remember in previous lecture, when I was telling you about the concrete cover thickness, how much, there was one case when concrete is exposed to earth permanently. This is the case. This is the footing case when concrete is permanently exposed to the earth. So here the concrete cover would be about 3 inch something, and then is the center of gravity of the upper reinforcement. Means that these are two reinforcement. From the bottom here you subtract the diameter of the first reinforcement, then the half of the upper reinforcement. So this comes to be 19.5 estimate. This is an the assumption or estimated. We assume the diameter of reinforcement here. So this comes to be effective depth. Assume effective depth. Don't get confused. It is assumed effective depth D. Next is effective soil pressure. So I make it again clear. Let's say this is our the bottom or top over here. From top to bottom, this one is 5 foot. This one is the 5 foot as given in the question statement here. 5 foot below the grade. So this one is the 5 foot. Now we have to determine the soil pressure QC. The soil is at this depth. So this depth of the soil is 5 foot minus this depth of the footing. So this is equal to QA, that is given to you, minus footing weight. Weight of the footing itself. This is the footing weight into fill weight. So footing weight is 2 times mean 2 foot. It is 2 foot, alright? Because we assume the thickness as 24 inch. So footing, this is 2 foot. That is inches, and here is 2 foot. And 150 is the unit weight of the RCC structure. So as it is reinforced concrete, so for its unit weight is 150, and the thickness of the thing is 2 feet. So it's, we got the footing weight, and then is the fill weight. So total depth of the footing from the grade is 5 foot. If we subtract 2 foot of the this slab or the footing, the remaining is 3 feet. Alright, 5 minus 2 is equal to 3 foot. And 100 is given as the 100 cubic pounds per cubic foot is given as the weight of the soil. So 3 foot into 100 cubic foot is the pounds per square foot. Alright. So the total effective, now this is the effective soil pressure. Actually the given one is the actual soil pressure is 500 pounds per square foot. But this soil, the given soil here, this soil has to support itself of this footing and the soil on this area. So this would not be used. So we have to subtract to find out the effective soil pressure. The effective soil pressure is the pressure that would support our building loads. This effective soil pressure would support the building load. So we subtract the loads of the footing weight and the fill weight. So then is the required footing area. How to determine the footing area required is, actually footing area required is based on the applied loadings divided by the effective soil pressure. Effective soil pressure is this one that we determine. Effective soil pressure that would resist the applied loadings, and the applied loading is given to you. Dead load 200 K and the live load is equal to 160 K, 160 kips and 200 kips. So this comes to be in total 200 plus 160 kilopounds per square foot is equal to 360 kilopounds per square foot, and this 4,400 pounds per square foot, that is equal to 4.4 kilopound per square foot. Keeps 4.4 keeps. Divide this one to convert into kilos with 1000, you will get 4.4 keeps, and this comes to be 81.8, and it's not exactly equal, but it's approximately 9 foot by 9 foot footing. Actually we are taking the square footing, so we will make it the all the dimension, both the dimensions same as the square one, 9 foot by 9 foot. So the bearing pressure for the strength design QU, that the ultimate design, that is, so we will find now the factored loads. You see, this is the factored load, 1.2 times of dead load plus 1.6 times of the live load, 1.2 times of dead load plus 1.6 times of the live load divided by total area, the total area, that is 81 square foot. So the ultimate the bearing pressure for the strength design comes to be 6.12 kilo pounds per square foot, kips per square foot. So the depth required for two-way punching shear. Now we have to check either the depth that we assume. We assume the depth, effective depth of D is 19 point something. We assume the effective depth 19.5. Now we have to check either this depth is suitable or compatible, or does this satisfy the criteria for the two-way punching shear. So we will determine the depth of the two-way punching shear, and similarly for the one-way punching shear. Actually there are more chances for the two-way the column square footing for the two-way punching shear controls the phenomena, and for rectangular footings the one-way shear or the beam shear controls the phenomena. So let's first determine this dimension. So this is the A1, the A, that is the dimension of the column, that was the 16-inch column. Then it was the D by 2 from both the sides. So D by 2 from the both sides mean how much is the D? D is 19.5 that we assume. Alright, we assume 19.5 D, and this is the dimension of the column, 16 inch. So it comes to be total 13.5 inch, that is 2.96 feet. Alright, the total comes to be 5.5 inch, and this comes to be 2.96 inches. So this dimension here is 2.96 inch. So we have to find the ultimate strength that produce the shear strength that produced at the periphery of this one. That is, you remember, is equal to the QU. Alright, the ultimate soil pressure multiplied by the hatched area. In the previous definition, when I told you what is the ultimate the shear strength at this periphery, that is equal to this QU, the bearing strength multiplied by the hatched area. So total area is 81 square feet minus 2.96 each square. So this is the hatched area. Actually this is the whole footing of you. This is the footing. This dimension of the footing is 9 feet. This is the 9 foot. So the square, this is the square, the area of this square is the 81 square foot. Alright, then we have to subtract this the shear area, the failure area. This one is the 2.96 square, 2.96 square. So this one is the hatched area into the QU, that comes to be 442 kips. This 442 kips. Now we have to check for the depth, effective depth. So using that formula given in the very first slide, here this formula gives the value of D 18.95, that is less than 19.5 inch. So it is okay. Because our assumed depth is quite okay. Similarly, using another formula given, there are three formulas if you remember. The previous one, maybe I can show you. This one, we are using this one here, D, to find out the D1. We are using from these things. Oh my god. So here we use the formula D, the one D formula we use here is to determine the thickness of the film. Similarly, this other formula and this value comes to be also less than the 6.1. And here is the other one which determine here. You see this is the other formula D, and this value also less than the 19.50. So this also satisfied the criteria, means our assumed value that was the 19.5 inch, the calculated values are, by the time the calculated values are less than D, that's okay for us. And here is one thing that we use, maybe you get confused, is 142. This 142 in the formula is termed as B naught, and it is calculated here. This B naught. This B naught is the the perimeter of the this area, and this area is the 35.5 inch, and this in terms of you multiply it by 4 and you will get 142 inch. So this is the perimeter of this here. So for depth required for one way or the beam shear, this one is for the two way or the punching shear, and now we will check the same for the one way. So one way, again this one is the 16 inch, the given dimension of the column, and we have to find out this value D we have assumed that is 19.5 inch. So we need to determine this dimension. So this dimension would be the total dimension from this center to this corner, center to extreme, is the half of the 9 foot. Half of 9 foot means 4.5 feet. Is the 4.5 feet. So the remaining this dimension would be 4.5 feet minus half of the column thickness minus D. That comes to be 3.83 feet. 3.83 feet. So now again using the same concept, that the QU multiplied by the hatched area. Hatched area is again here 9 foot is this dimension, and the other dimension, this one hatched area, that is calculated over here, that's 2.208 foot. So 2.208 foot over here. So this come to be the shear strength of the this section, hatched section here. Similarly, we determine the value of D, and that also comes to be 19.5. So here comes all the dimensions that we have calculated are less than the assumed value. Assumed value that was the effective, that was a 19.5 inch. So it's okay. So this check recommends us to use the 24 inch as the total depth. Actually, this 19.5 inch was calculated based on this assumption of 24 inch total depth. So once we apply these checks, so these checks are okay, and this recommends to use 24 inch as the total depth. So now determine the moments and 5 BD square total. MU is 404. That's I think calculated somewhere. Yes, 12 into 404 and 5 BD square. MU is yeah. So using 24 as a total inch depth, we will determine the MU over 5 BD square is come to be 131.2 pounds per square inch. 131.2 pounds per square inch. So if we check from the table for the row value for this case, if we check from the table for the row value, and do remember one more thing, these tables for the slabs are different than beams. I think I haven't provided that so far, so I would give it to you. So the raw value for the slab in case of this one, this value mu5 BD square comes to be less than raw minimum in flexure. For flexure, if you see there in the tables, there would be one value of given the raw minimum for flexure. So our value should be more than this flexure. So if in case the calculated value comes to be less than rho minimum flexure, then we have to take the larger value of these two things. The larger value of these two things is 200 over 60 Fy, 200 over Fy plus under root 3 Fc prime over Fy. So if in case the calculated rho value comes less than the rho minimum for flexure, then we have to use the larger value of F. This is 200 over Fy, and this is 300 Fc prime over Fy. So the larger of these two is 0.002, and interestingly this larger value is the same as of rho minimum for the flexure in the table. So anyhow, we can use for this one this 0.003 value. So using this value we determine the area of steel required. Using this value we determine the area of steel required, and the area based on this area of steel required we find out the numbers of parts and the size of the parts. So that's all for the design of design of isolated shear footing. Similarly, there is a bit concept of isolated rectangular footing, but the design procedure is almost identical and the same one as of the shear footing. But in this here, after once we determine the required area is calculated and the lateral dimensions are selected, the depth required for one-way or two-way shear are determined by the usual method. Similarly, as we determine for one-way and two-way shear, we determine the same one. But the difference is in here, in rectangular section, the amount of reinforcement distribution, the distribution of the reinforcement is different. This is called the band width. This dimension, this is the full width. This is the full length of the isolated footing, and this one is the width of the footing. So this is the width of the footing. So in this case, in case of the rectangular strip, this band width requires more steel reinforcement here. In this area, we provide more reinforcement here because this area takes the larger percentage of load. This area takes the larger percentage of load, so that's why more reinforcement is required here. The amount of reinforcement in this band, this is called band. Alright, in this band is to be determined with the following expression. This one is the expression that we use, that's ACI 15.1 equation. So using this phenomena, using this band width, we determine how much steel is to provide in this area for the longitudinal direction. So for this formula, it is 2 over beta plus 1. 2 and 1 are the simple numerical factors, and beta is again the ratio of length of the longer side to the width of the shorter side. Alright, length of longer side to the width of the shorter side. That simply mean longer side over the shorter side. So here comes for the isolated rectangular footing. Simply design a rectangular footing for an 18-inch. There was a 16-inch. Now it is 18-inch square interior column. Square interior column with a dead load of 185 and a live load of given. Make the length of the longer side. Oh, it's recommended. Sometimes you take on your own, but here it's recommends the length of the longer side equal to twice the width of shorter side. So you are restricted. So your dimension of this rectangle should be that the longer side should be 2 times of the shorter side. Fy and Fc prime are given. Qa, that is the actual load, is 4000 psi. So we have to proceed the same way again as we did in the shear footing. All the process is the same. We assume that thickness and then determine the effective D, and here then based on this we determine the effective depth, effective soil pressure, that is the actual soil pressure, and we subtract the soil subtract the loads of the footing, and we subtract the loads of the soil on the footing, because here it is again mentioned somewhere that it is 5 foot. Assume the base is 5 foot. So 5 foot is the total base of the footing. Then 2 feet we assume the thickness of the slab or the footing. So remaining is 3 foot. 3 foot is 36 inch simply. So it's 3400 psf. It means 3.4 kips. And the required area of the required is 98.5 feet square. As it is restricted from the question that the longer dimension should be 2 times of the shorter dimension. So if we take the shorter dimension as a 7 foot, the longer dimension would be 2 times of this one, that is 14 inch. So that also comes to be 98 square feet. Preferably try to be more than the 98.5. I mean upper side would be okay, but if you are as close, you see it's 98 square foot and this is 98.5 square feet. Better to go for the upper side. If a very less difference between the lower side, then is okay. So the ultimate strength, the QU again is the factored loads divided by the area, and this gives you the 4.71 kips per square foot. Again here the depth required for one way or beam action. B is the 7 foot. This depth is the 7 foot is the depth. Now VU is the QU multiplied by the hatched area. Now hatched area is this one. This one is the the center line. So we have to determine this hatched area dimension, because this is known to us, that is 7 foot. Now we have to determine this dimension. So this dimension would be from here to here. It is 3.5. 7 foot. This is 7 foot. From here to here it is 7 foot. And this dimension from here to here is known to us, that is half of the column dimension. Column full dimension is 18 inch and the half of the column is 9 inch. So now from here to from here to here it is 7 feet minus 9 inch. It is 7 feet minus 9 inch. So 1 minute please. So this is 7 foot 9 inch. Now we know this dimension. This dimension is the D. This dimension is equal to D. So D is this one. So the remaining dimension is now 7. This dimension is 7 feet minus 9 inch minus D, and that comes to be 4.62 feet. This comes to be 4.62 feet, and 4.62 feet is here. Width into length 7 feet. This is the total area of this hatch section. So this hatch section area multiplied by 4.71 is equal to 152.4 kips, and using the D value we determine here 9.14. Using the same formula there before, 19.14 inch we determine. For two-way punching shear. Yes, one more thing, don't get confused here. In the rectangle, in the square section, first we determine the depth for the two-way punching shears, and later we find for the one-way. And as I spoke earlier, for square columns, the section is controlled by the two-way punching shear. Sorry, but in rectangular section, it's controlled by the one-way shear. So that's why we first check one way. If one way fails, we will. If one way fails, let's say it comes to be more than our assumed value, then we definitely increase the value before we go for the further calculations. So here now, for two-way, similarly B naught is 4 into 37.5 inch, and here is 37.5 inch. That is equal to how much? How does calculate? It's here. It's 3.125 inch, and again this area, shaded area, is 98 is the total area, and 3.125 subtracted. That is the remaining shaded area. This shaded area you see here. This shaded area is come to be 14.6 inch square, and from here we find the determine the value of D. That comes to be 11.52. So this D also comes to be less than this D is also less than our value of D, that is 19.5, I guess. That is 19.5. So it means the depth we assume for the thickness of the slab or the footing is quite okay. So 24 inch we can continue. Now here is one thing that is different from the so far what we have calculated is the similar as in the square footing. Now here it comes a difference one here. the lever arm. We need to determine the moments and all these things. The lever arm. Now the lever arm for the longitudinal steel. We have to find no we have to determine two kinds of steel. One for the longitudinal direction and other for the transverse direction. Let's say this is our here. So the steel reinforcement in this way are the longitudinal steel reinforcements, and the other way are the transverse reinforcements. So the longitudinal reinforcement, for longitudinal reinforcement we need to find the lever arm. So lever arm is how much, let's say, let me change the color, I think that would be more okay. So this is column here. Actually we have to find the moment at the center. So this dimension is 14, okay, and from the center here or whatever, this is the 14, and this column dimension is itself 18 inch. So the moment placed at this surface, at the face of the column, would be half of this 14 by 2 minus 9 by half of the column thickness. Maybe you're not clear, very clear. I try once more. We need to determine the moments at the surface of the column. This is column. We need to determine the moments at the surface of the column here. So the total length is the 14. All right. So let's say this is the center. This is one extreme. So we need to find the moment arm from this to this one. All right. So from here to here, this dimension is the 7 feet. 7 feet, or you can say 14 by 2. All right. So we need to determine this one. So this one, we would subtract this area from the 7 foot, and this area, this dimension, this thickness is half of the column thickness, 9 by 2. So the remaining area, remaining length dimension, this one, that comes to be 6.25. That is the moment arm. So the moment produced here is 6.25 into 7 into 4.71. 4.71 is simply against the earth pressure, soil pressure, that's this, and 6.25 and 70 is the hatched area. All right, it's just area, the other side of the column, face column, and this we multiply with the moment half of the 6.25, this dimension, half of the this moment. Let's say I make it very clear further again. This one here. Here is the column face, and this is the column here. All right, don't get confused. This is column. Now this is footing. So this is from here to here. It's 6 point something. That is 6.25 here. So this is vertical loads acting on, let's say. So the moment produced over here would be equal to, actually it is soil pressure, not vertically downward, actually it is vertical upward soil pressure. All right, 4.75 applied on this area, 6.25 into 7 area, and then this moment produced over here, and it would be at the center rectangular. So this would be 6.25 by 2. Clear? So it comes to be 643.92 foot. So mu over 5 BD square is 268. And from the table A13, that's I have given to you A13, I guess. So from that table you can determine the rho value, and using this rho value you determine the area of steel. So this area of steel is for one direction, So use 10 number 8 bars in the longitudinal direction, this direction. All right, use 10 number 8. Now we have to move for the transverse direction. So for transverse direction, again we will determine the lever arm. So here the lever arm is again the same calculation way, but in the other way. So now we have to calculate the lever arm in this one here. This one, you can say this is our lever arm. So this would be 7 by 2 minus again 19 by 2. This would be the lever arm, and using again the same concept, area into the SKU and into half of the lever arm, that will give you the moment along the face of the column, this face of the column. Previously we determined the moment at this face of the column. Now we are determining at this face of the column. So we got this moment using this moment. Now here is again the same point. You see, use larger of this one again. Actually, when we determine using this one, this value comes to be the row value for this comes to be less than row minimum for the flexure. This value comes to be row minimum than the flexure. So that's why here it is recommended that use larger of 200 over Fy or 3 times of Fc prime over Fy. So between among these two, this is again greater one. So use 0.003. So use 0.003. Area of Shear is equal to rho BD. So using this one, this comes to be area. And here it recommends 18 number 7 bars for this longitudinal direction steel. So 18 numbers 7 bars in longitudinal direction. So one more thing there was that I remember, the band width, the band where we put more more reinforcement at the column. This is the column. If so, this is the band section, bandwidth. So here longitudinal reinforcement concentration is more, alright, more closely spaced and more reinforcement is provided here than in the sides. So this band B, how much reinforcement to provide here is just simple. Using this warmer reinforced in bandwidth is 2 divided by total reinforcing in short direction is 2 over 2 plus 1. So this 2 is of the beta value, I think. This 2 is the beta value, and here is the 2 over 1, the formula given by the formula. So it's 2 by 3. So 2 by 3 of the 2/3 of the 18 bars. Alright, 2/3 of the 18 bars comes to be 12 bars in bandwidth. So you see, in this area only, in this section only, you have to use 12 reinforcement bars and the remaining 6 bars on this area. 3 this way and 3 this way. So this is the design of the transverse steel. And so it was the complete now. This was totally the design of shear footing, isolated shear footing and the rectangular shear footing. So hope you understand. You try. If you get, very good. If you didn't get, you just get back to me. Inshallah, I would repeat for you and I would make you clear. You have any query, you can just drop me an email. You can just comment below this video, so I would answer you inshallah. Okay, take care. Allah Hafiz.